After studying this module, you shall be able to know about the basic structure of an exponential function, understand how growth rates are calculated, understand the properties of an exponential function, and estimate an exponential function and the growth rate through the exponential function. First of all, let us look at the class of nonlinear functions. It consists of the inverse function, the quadratic function, the cubic function, the Gompertz function, the logistic function, and the exponential function, which we are now examining. In this module, we are considering the properties, path, and estimation of the exponential function. We would also learn how to estimate the compound growth rate with the help of the exponential function. The most useful function for doing growth analysis is the exponential function. Various economic variables like GDP, money supply, consumption, etc. all need to be measured in terms of their growth rate over a period of time. Here, exponential function comes in handy. First of all, let us look at the exponential function whose general form is like a growth function. By definition, the general form of the exponential function is f of x is equal to b to the power of x. Therefore, x as a variable appears in the exponent or the power term. Similarly, we could also say that f of x is equal to bx plus or minus c could also be an exponential function. This is because it is derived from the function f of x is equal to e to the power of b plus minus c, which could be rewritten in logarithmic form as a logarithmic transformation as f of Lx is equal to bx plus minus c. That is, when we take the log of both sides of the equation, then the right hand side becomes a linear function, and this is known as the log linearization. Here L stands for log to the base e and not log to the base 10. Exponential functions are generally classified as growth functions. They are characterized by the fact that they can capture growth rates directly. So we have the differentiation of b to the power of x with respect to x, which is equal to b to the power of x into a constant, where the constant stands for the intercept term and where the base is the number e, which is approximately equal to 2.71828. Therefore, we could also say that the differentiation of e to the power of x with respect to x is equal to e to the power of x into 1. Here, this is known as the natural exponential function and can be expressed in the following manner. As x tends to exp x, so the x variable tends to become the exponential of its own. The exponential function model has been defined and it has a definite structure and purpose. The general form is that it is defined over time. Therefore, we could consider variable yt and which would be equal to e to the power of a plus bt. This is the general structure. The structure is that any variable that is regressed on time has got a constant growth rate which is equal to b. Now let us see how we derive this growth rate. Usually it has an intercept that tells us about the minimum level at which the phenomenon yt is being measured. The variable yt could be income, prices, consumption, etc. The purpose is to enable the determination of the growth rate, usually treated as the exponential growth rate. The relationship between yt and t is that yt grows in proportion to t, that is time, over a period of time, and it changes over a period of time proportionally to time itself. Growth rates. How do we compute the growth rate with the help of an exponential function? Once again, we consider the function yt is equal to e to the power of a plus bt. Taking natural log of both sides, we arrive at the log linearized version of this exponential function, which is L by t is equal to a plus b into t. Please note that here capital T is not the subscript, but it is a variable which stands for time. If it is annual data, then we will treat this as years. It could be monthly, quarterly, or even daily data. So time refers to the variable at a given point of time. Now L by t minus 1, here t minus 1 is a subscript, is equal to a plus b into capital T minus 1. Here t minus 1 refers to the variable time at point t minus 1. So subtract equation 2, which is the value of yt minus 1 from the value of yt, then you could notice that L by t minus L by t minus 1 is equal to bt minus bt minus 1, which is the same thing as b. If since on the right hand side we basically are left only with b, therefore on the left hand side if we say yt minus 1, then in log terms this would actually be the log of yt minus upon yt minus 1. So what would log of yt upon yt minus 1 mean? It means how the variable y is growing over a period of time, over one period of time. It could be 1 year or 1 month or 1 day, whatever is the measurement of time, and this is equal to just b. So b is nothing but the growth rate. Now in terms of a regression equation, b is always treated as delta y upon delta x. Here delta y is yt upon delta x. Here x is not x but it is time. Therefore b is equal to delta yt upon delta t, and we know that delta t is addition of one time period, which is simply 1, and delta yt is nothing but the change in the left hand side variable, which is log of yt. This could be expressed as log of yt upon yt minus 1. In other words, the left hand side is telling you about how the variable yt is growing every year or every month or every day, as may be the case, and on the right hand side we say that it is equal to b. Therefore b is nothing but the growth rate of the variable yt during 1 year. The growth rate therefore, if measured in annual terms, would be the annual growth rate of the variable yt. Now this could be expressed as yt is equal to y0 into 1 plus r to the power of t. R is the rate of growth, and this is comparable to a compound interest formula, and hence taking log of both sides, this would mean that yt is equal to log of y0 plus t log 1 plus r. And when this is simplified, then we could rewrite it as a linear equation, that is yt is equal to b0 plus b1 into t. And from this it becomes clear that b0 is log y0 and b1 is log of 1 plus r. So here if we take the antilog then of b1, this is antilog of log 1 plus r. Therefore, on the left hand side we have antilog b1 which is equal to 1 plus r, and if we minus 1 from both sides, then antilog of b1 minus 1 is equal to r. R is nothing but the growth rate of yt. Therefore, here of course we must note that there are two growth rates. One is the first growth rate, that is b1, which is known as the instantaneous growth rate. On the other hand, antilog b1 minus 1 is the annual compound growth rate, or ACGR, which you would encounter in many articles. What are the different forms of the exponential functions? The exponential function e to the power of x can be characterized in a variety of equivalent ways. In particular, it may be defined as the f of x is equal to sigma n ranging from 0 to infinity x to the power of n upon n factorial, which is equal to 1 plus x squared upon 2 factorial plus cubed upon 3 factorial plus x4 upon 4 factorial, and so on. Using an alternate definition for the exponential function leads to the same result when expanded as a Taylor series. Less commonly, e to the power of x is defined as the solution of the y from the following equation, that is x is equal to integral 1 to y 1 upon t dt. It is also the following, has also the following limits, that e to the power of x is equal to limit n tends to infinity bracket 1 plus x upon n whole bracket closed to the power of n. The exponential function will look like this as we look at it in an asymptotic manner. You would notice that on the y axis we are measuring f of x, which is in this case equal to 2 to the power of x. Therefore, our base is 2 over here. What does this imply? This implies that as we move from 0 to the positive quadrant away from the origin, that is towards plus infinity, then the function keeps doubling, and as we move to the left from the origin towards minus infinity, then the function keeps halving. So what happens is that it becomes smaller and smaller till the time that it almost approaches 0. So these are some of the asymptotic properties. Let us again have a look at these properties. If we plot a graph of the function f of x, which is an exponential function, y is equal to f of x, which is equal to the power of x. So as we go away towards the negative axis away from the origin, f of x keeps halving. Therefore, the exponential function starts from a very small fractional number and it almost touches the x axis. In the beginning, y is extremely small, and then it almost becomes, y becomes equal to 0, and therefore it is almost touching the x axis. Once y starts growing faster and it accelerates, and once it comes into the acceleration phase, which is in the positive quadrant, the term, the exponential growth, actually implies this very pattern, starting very low, and for a long period it will remain low, and then it will suddenly start growing. In our case, because the base is 2, then after it comes into the positive quadrant, for every single unit change in x, then y would start doubling. So therefore it would result in very rapid growth. So if we look at the increment in y for each x, in this case we could also substitute x with t. So for each time period, when the movement is from 1 to 2, then the growth is 2. The movement from 2 to 3, the growth becomes 4. From 3 to 4, the growth becomes 8, and so on. All of these are shown in figure 1. Now let us look at the properties and restrictions. First of all, we have an interesting figure, that is figure 2, which shows the nature of the exponential function. If we concentrate on the exponential function in the vicinity of the origin, you would notice that to the right in the first quadrant, if x takes the value 1, then the coordinates of y coordinates are 1 and e which is the natural base e. And if you look to the left, that is, if you look at the origin, then at the origin the coordinates of the exponential function are 0 and 1. That is, when x is equal to 0, then the exponential function is equal to 1. When x is equal to 1, then the value of y, or the exponential function, or the height of the exponential function, or fx, is equal to e. This is a peculiar feature of the exponential function. Therefore, now let us look at the asymptotic properties. The path of the exponential function from minus infinity to plus infinity starts from certain values. Suppose if x is equal to 0, then f of x, as we know, is equal to b to the power of x. Now we replace these values. F of 0 is equal to b to the power of 0, which is 1. If x is equal to 1, then f of 1 is equal to b to the power of 1, which is b. And we know that the base is the natural log, which is e. When we look at the function, when x approaches from the origin, that is from minus infinity, that is, as x approaches 0 from the left hand side, then f of 0 approaches 1. The coordinates of x and y therefore are 0 and 1 when x approaches 0. When x approaches the origin from plus infinity, and therefore x is approaching 1, then f of 1 is equal to b or e. The coordinates of the function x and y over here are 1 and e. So these are the coordinates that have been shown in figure 2 above. If b lies between 0 and 1, then the exponential function would be downward sloping. If b is greater than 1, then it would be upward sloping. Now in figure 3, you could see decaying function. In this case, the function gx, which is a growth function, is equal to 0.5 to the power of x. We notice here that b is smaller than 1, and therefore you would see that the green line, which is an exponential curve, but it is a decaying curve. The above function is based on, as we have said, g of x is equal to 0.5 to the power of x. Since b is less than 1, the function is decaying. It moves downwards from the left to the right, shown in figure 3. Some restrictions. There are some restrictions on the parameters that influence the exponential function. the first restriction is on the extreme values of b. We must avoid 0 and 1s since the log of 0 and log of 1 are both constant, and therefore we won't have many of the properties that we actually desire from an exponential function. Thus, f of x is equal to 0 to the power of x, which is equal to 0, f of x is equal to 1 to the power of x, which is 1. Hence, it is necessary also to avoid negative numbers for b. This may lead to imaginary numbers. For instance, suppose we consider b is equal to minus 4 and x is equal to half. X is equal to minus 4 to the power of half. So, under root minus 4 would be an imaginary number. Therefore, this is one more restriction on the exponential function. Now, let us look at some comparative functions. Before estimating the exponential function, we must first be clear about what is the distinction between different functions. Therefore, we consider three possibilities: the linear, polynomial and exponential function. The linear function is of the form y is equal to 5x, and the polynomial is of the form y is equal to x squared plus 3x, and the exponential function is y is equal to 1.5 to the power of x. The slope of the linear function we know is constant. The slope of a polynomial function is gradually it increases. The slope of an exponential function is initially very low, slow, and suddenly it increases. And if we look at x in both directions, towards the right the function in the case of an exponential function suddenly increases, towards the left it suddenly decreases. At x equal to 12, the height of the quadratic is more than the exponential function, as you could see in the figure which compares all these functions. Then if we look at the x is equal to 9, even the linear function is higher than the exponential function. But when we look at x is equal to 10, then the exponential function suddenly increases in height. These relationships are given in figure 4, and you could examine what has been said above. There are certain points at which the exponential function shoots up and crosses both the linear function as well as the polynomial function. But at low values of x, both the linear function as well as the quadratic function are taller, are higher than the exponential function. Of course, negative axis, on the negative axis in the second quadrant, of course it is difficult to make such comparisons. Estimation of the exponential function. We shall estimate the empirical exponential function and estimate the growth rate. As we have seen here, there are two growth rates: the instantaneous growth rate and the annual compound growth rate. You have a figure here, figure 5, which is an estimated function of India's GDP growth over a 20-year period. We have used a semi-log equation. The original equation, the algebraic form of the equation, is GDP is equal to e to the power of a plus bt. When we log linearize it by taking log on both sides and adding an error term, it becomes log of GDP t subscript is equal to a plus b t capital, which is year, plus ut, which is t subscript again. So, figure 5 shows how good an estimate we have arrived at, because the growth path is depicted with the help of two lines. One is the actual GDP growth path and the other is the predicted. The predicted is obtained from the semi-log equation once we have estimated the equation with the help of regression. The instantaneous growth rate is the growth rate at a point of time, whereas the annual compound growth rate is the growth rate for the entire length of time, let us say 20 years, the instantaneous growth rate would be the slope at a given point, let us say 2000, whereas the annual compound growth rate would be, let us say, from 1991 up to say 2000 or 2010. Coefficient that has been obtained by estimating the regression equation says V is equal to 0.1325. We have to multiply this by 100, so the growth rate is 13.25%. The annual compound growth rate, on the other hand, is anti-log B minus 1, which happens to be 14.16% per annum. The ACGR is 14.16% per annum. The estimated equation is expressed as log GDP subscript T is equal to minus 234.37 plus 0.13249, which is the coefficient or the growth rate, into T plus UT. The T statistic for the intercept is minus 49.48 and the T statistic for the coefficient is 56.14. So the table 1 shows that the R square is pretty high, and so it is a good fit, and the coefficients are, as we have already mentioned, the main interest is in the beta coefficient is 0.13249. So this is our India's GDP growth equation. As a summary, we can say that the nature, length and shape and properties of the exponential function have been discussed here. The basic structure of the equation of a exponential function is f of x is equal to b to the power of x. There are two types of growth rates, the instantaneous and the compound growth rate, both of which have been understood and calculated. The instantaneous growth rate is at a point of time, whereas the annual compound growth rate is over a period of time. We have understood the properties of the exponential function, which follows a path from minus infinity up to plus infinity, and when it approaches from minus infinity and it approaches 0, then when x is equal to 0, then y is equal to 1, and when it approaches from plus infinity and x approaches 1, then f of x is equal to b, or which is e, or the natural log. The coordinates we have seen accordingly. Then with the help of a semi-log equation, we have estimated the growth rate which defines the growth path of India's GDP through an exponential function.